All right, welcome everyone. Today we're going to continue on talking about integration by parts, specifically for indefinite integrals. And we're actually going to see some kind of more complicated examples where we might have to do integration by parts twice. We might have to get a little creative in how we view our function or our integral. But to get us going here, we're going to look at example 3. This is kind of more standard fare in terms of integration by parts, just to get us kind of back into the groove here. All right, so what are we going to do in this one? Example 3. We're going to integrate the function x squared times natural log 2x. All right, so first thing we want to do is just kind of think about the pieces or the parts of our function. And it helps to just kind of write these out. So what are the two kind of pieces of our function? Well, we have an x squared and we have a natural log of 2x. And let's remember what the first step of integration by parts is. Step 1, we need to choose u and calculate and choose dv. So we're going to choose u, choose dv, and one of our strategies for how to do this was with that acronym. So let's write the acronym at the top here, LIATE. Logs, inverse trigs, algebraic, trig functions, and exponential functions. And then we just go through and we look at the two pieces of our function and we classify them. So x squared here, this is an algebraic function. So we have one of the pieces of our function is algebraic. Then we go to the next piece, ln of 2x, that's a log function. And that's over here. And the way we use this acronym is we kind of think of it as a almost like a continuum. The things further to the left are what we choose for u, and the ones further to the right are what we choose for dv. So if we're looking at this thing, the log piece of our function is furthest to the left, so that's what we're going to pick for u. So we're going to pick u equal to natural log 2x. And then dv, that's an algebraic function. That's further to the right of our two pieces. So we're going to let dv equal x squared dx. And that's it. That's how we choose u, how we choose dv. Now, the one thing to note here is that when we make those choices, if we put them together, we have our original integral. So everything has to be accounted for in our choice for u and dv. We can't leave things out. All right, so now step 2 is to calculate du and calculate v. So to get du, we're going to differentiate. And this one might be, we have to remember our derivative rules here. So it's not just natural log x, it's natural log 2x. So a little chain rule comes in. So derivative of the outer function is 1 over 2x. And then we multiply by the derivative of the inner function. So derivative of 2x. And then we also multiply by dx because we're calculating a differential. Clean that up. Derivative of 2x is 2, and then the 2 cancels with the 2 in the denominator. So we end up with 1 over x dx here for our du. All right, so we differentiated to get du. Now to get v, we're going to integrate. So the antiderivative of x squared is 1/3 x cubed. And there we go. We have all of the little ingredients now that we need for our integration by parts. So now step 3 is to put them all together using our integration by parts formula. All right, so how do we do this? Well, u times dv is the original integral. So that's what we're kind of doing originally. It's dv is x squared times u is natural log 2x, and then we have our differential at the end. So that's u times dv. And what the formula says is that that's equal to u times v. So let's write u times v. And to keep things nice and tidy, we're going to put the 1/3 x cubed in front of the natural log when we write that. So 1/3 x cubed times natural log 2x. Then we subtract and integrate, and v times du. So that's the integration by parts formula. The integral we want to calculate is equal to u times v minus the integral of v times du. So v was 1/3 x cubed, and then du was 1 over x dx. And that's it. We've applied the integration by parts formula. And what we've done is we've started with a complicated integral there on the left, the one we're trying to do. And using this formula, we've produced an integral. We still have to do some more integration, but now that integral that we have to do doesn't have a natural log in it. So hopefully it's going to be a little bit easier. And let's see how we're going to do this. And we still have a product here, so we still have to do something with these x terms. And what we can do is we can actually do the multiplication. Essentially they're just power functions, so we can do the multiplication. So we can't just integrate them there because it's a product. We can't integrate products like we want to. It would require integration by parts, but here we can actually just do the multiplication, and some of the x's cancel. So we still have that part in front, the 1/3 x cubed times natural log 2x. We're done with all the integration there, so that's not going to change at all. And then simplifying the integral, the x cubed times the 1 over x, that's going to simplify to just x squared. And now that's doable. That's just another power rule. So the last step here is to just finish integrating. So we have our 1/3 x cubed natural log 2x. We're done with that. Our minus 1/3 is a constant in front, so that's just going to stay in front. And then we find the antiderivative of x squared, so our variable is x. We add 1 to the exponent, takes us up to 3. Flip that new exponent, put it in front of the x, and there we go. So we have our antiderivative now. And maybe the only thing we could do a little bit further there's a little factoring we could do if we really wanted to. We could factor out a 1/3 x cubed. We could multiply those 1/3s together, but that's fine. So we'll stop there. That was step 4. Finish the integration. All right. So let's so that was more standard fare. Just using the acronym to help us choose u and dv. Let's see an example now where we have to get a little creative in how we kind of set up the problem. And let's go in with the mindset that a lot of times we use integration by parts. What we're seeing is a product of two functions. And, here we had x squared times natural log 2x. So there really was no really complicated inner function. Yeah, there was the 2x there, but that's not a really complicated inner function. So really all we had was a product of two functions of x. And so that's an indication that we might need to use integration by parts. In this next example, though, we're not going to see a product, at least immediately. So in general, kind of one of the nice side effects of integration by parts, one of the nice benefits, is that we can use it to integrate our inverse functions. So we can use it to integrate inverse trig functions, but we can also use it to integrate inverse exponential functions, which also happen to be called log functions. So we're going to use integration by parts here to integrate natural log x, something that looks like we should have been able to do already, but we haven't. You know, if you go back to our list of basic integrals, this one is kind of noticeably absent. So it's kind of surprising. And the reason is because we need integration by parts to be able to do it. So let's see the strategy for how we would handle something like this. And the trick, it really comes down to a trick. Is to rewrite our function. Right now it's just one function. We're going to rewrite it as a product. And namely, it'll be natural log x times 1. So we're thinking we have a part here of our function 1, and we have a second part here, the main part, which is our natural log. Now we see it as a product, so we're thinking maybe integration by parts might work. So we go to our acronym, and classifying these, we know natural log is a log function. And what is 1? Well, that's just an algebraic function. And so, again, the one further to the left, that's what we pick for u. And the one further to the right, that's what we pick for dv. So when we set this up, in step 1, we're going to let u equal the natural log of x, and we're going to let dv equal 1 times dx. There we go. Step 2, we're going to calculate the remaining pieces that we need. So calculating the differential du, we do the derivative of natural log x. It's just 1 over x multiplied by dx. To calculate v, we're going to integrate 1. So the integral of 1 is x, 1 times x. And there we go. We have all our pieces now. So now we can, step 3, we can use the integration by parts formula. So if we multiply u times dv, that gives us our original integral. And that's going to be equal to u times v. So let's write that down. And it's good to put kind of the natural log term last, just so you don't kind of get the pieces mixed up. So it's x times natural log x. Then we subtract and integrate. And we integrate v times du. So x times 1 over x dx. And that's step 3. Use the integration by parts formula. And now we have to finish that remaining integral. And we know x times 1 over x can be simplified by just doing the multiplication. So if we do that, it just ends up the x's cancel and we're left with just the 1. So we end up with x times natural log x. We're done with that first part. Minus the integral of 1 dx. And the integral of 1 is 1 times x. So it's just x. and then we put our plus c at the end. And there we go. We have our antiderivative now. So we were able to kind of, it doesn't look like we'd be able to, it's kind of surprising, but we were able to use integration by parts to calculate the integral of this log function, this inverse function. So it's kind of nice. So if we had an inverse trig function, you'd kind of use the same trick to get you started using integration by parts. All right. Let me check something. Okay. Just wanted to make sure. I was thinking about it. Make sure I put the plus c at the end for example 3 as well. We're doing indefinite integrals, so we don't want to forget that. All right, let's try another one. So, and before we get there, it'll be just kind of helpful. We mentioned this yesterday, but it'll be helpful to mention it again. We have these kind of K-form integrals, and I've listed a few here. So we're going to kind of use these. These will be helpful. And you can prove each of these if you want the practice. You can prove each of these using substitution rule, where you set u equal to k times x. So essentially in these forms, k times x is the inner function. So for instance, in the first one, we have the integral of e to the kx, and calculating that antiderivative really is a substitution problem, but it's this nice, almost relatively easy formula to remember. So you'll probably just start remembering these as you do these problems. So how to remember it? Well, we integrate e to the kx. We get e to the kx, and then we take the constant that's in front, flip it, and put it in front of the exponential there. And this only works, so the note here is these only work when our inner function is k, a constant, times x. If there's an x squared, if there's an x cubed, if it's square root x, if it's any other kind of x term, it becomes more complicated. So this only works if the inner function is k times x. So it just has to be an x. It can't be x squared or anything like that. So same for like sine of kx. We take the constant k, flip it, put it in front. So that's where the 1 over k is. And then we integrate sine like usual. So what's the antiderivative of sine? Well, it's negative cosine. And then we keep the inner function the same. Integral of cosine kx. Take the constant that's in front of the x, flip it, put it in front. And then what's the integral of cosine? It's sine. And it's sine of the same inner function. So these are just, formulas that we'll see enough where it's just handy to have these memorized. But like I said, if you wanted to, you could go back, use substitution rule, and prove each of those. All right. And we're going to use that. Oh boy, there we go. We're going to use that in example 5. So we're going to integrate x squared times e to the negative 2x here. And in this example, we're going to see that sometimes you have to do integration by parts more than once. All right, so let's start this one off. Let's look at the two pieces of our function. We see that we have a product, so it's x squared times e to the negative 2x. There's no really complicated inner function here, so it's not so much a substitution rule issue. So we then go on to the next method that we've learned, integration by parts. So we see a product. There's no obvious complicated inner function here, so the next thing to try is integration by parts. And we're going to use our usual acronym LIATE strategy. Let's classify the pieces of our function. So we have, what do we have? We have this x squared. That's algebraic. And then what else do we have? We have this e to the negative 2x. That's exponential. And how does this strategy work? Well, the piece that's further to the right, that's what we pick for dv. The piece that's further to the left, that's what we pick for u. All right, so let's do that. So step one, we're going to choose u and dv here. So we're going to let u equal our algebraic piece, x squared. We're going to let dv equal our exponential piece, e to the negative 2x dx. We have our choices there, so now we calculate. So we're going to calculate du. We're going to calculate v. So to get the differential du, we do the derivative, so we get 2x and then dx. To get the integral of e to the negative 2x, that's one of our k forms. So the exponential part stays the same, and then we take the constant that's in front of the x, in this case negative 2, and we flip it and put it in front. So we get negative 1/2, do the reciprocal. All right, so we have all of the ingredients. So now we do our integration by parts formula, which says u times dv, that's the original integral that we're trying to do. That's our original integral. And integration by parts says, well, that's going to be equal to u times v. So we multiply along the diagonal there. So let's multiply those together. And to make this look nice, I'm going to put the negative 1/2 first. Then I'll put the x squared. And then I'll put my e to the negative 2x. So you just kind of move the order a little bit as needed there. All right, so that's u times v. Then we subtract and integrate v times du. So let's write that in. So we're going to have negative 1/2 e to the negative 2x times 2x dx. And let's simplify that down a little bit. And that was step 3. That's using the integration by parts formula. So let's simplify that remaining integral. We know we still need to do it. I see a lot of negatives, see a couple constants that might cancel. And it's good to simplify things as you go, especially with integration by parts, because you're going to end up with a lot of negatives floating around. Just it's the way it goes. So if you end up with double negatives, it's usually helpful to just try to simplify those as you go, so you don't have so many negatives. And that's what we're going to do. We're going to have this piece, which we're done with. That's not going to change at all. We end up with a double negative here, so those are really just going to cancel, become just a positive. And then we also have a 1/2 and a 2, so those are going to cancel. So this remaining integral is going to become the integral of x e to the negative 2x. And, you know, when I write these, I like to put the x term first, then the exponential term second. Just looks nicer in my opinion. It also is... The x term tends to move around, so you don't want it kind of drifting up into your exponent when you're writing these out. All right, so that's our remaining integral. And if we look at that, it's another product. It looks sort of similar to the one we started with. We started with x squared times e to the negative 2x. Now we have to do this integral of x times e to the negative 2x. The only difference here is we went from an integral with a x squared. Now we've gone down a power, so we have an integral of just an x times the exponential. So it looks like we're making progress, but it's still a product. There's still multiplication in there. And so that's an indication that we're going to have to do this again. We're going to have to do integration by parts again. All right, so let's do it. So let's we're going to work on x e to the negative 2x. We're going to choose, we need to choose u. We need to choose dv. We're going to be consistent in how we make these choices. So we from last time, we knew we let u equal the algebraic part, the x squared. So we're going to do the same thing here. We're going to let u equal the algebraic part, x. We're going to let dv equal the exponential part, e to the negative 2x dx. And then we're going to calculate the differential du. So what is the derivative of x? Well, it's just 1. So we end up with 1 times dx, or just simply dx. We integrate v, or we integrate dv to get v. And this is just another k form. It's the exact same one we did before. So we end up with negative 1/2 e to the negative 2x. And we're going to use integration by parts again, the formula again. So multiplying u times dv, that's what we're trying to do. That's the integral we're trying to do. And it's going to be equal to u times v. So let's write those in, negative 1/2 x e to the negative 2x. So that's u times v. And again, I like to put the constant multiple in front, then the x term, then the exponential term. Looks nice, in my opinion. And then we're going to subtract and integrate v times du. So v is negative 1/2 e to the negative 2x. So we're going to be doing this integral of negative 1/2 e to the negative 2x. And we have another double negative. So let's clean that up before we actually get to the integration. We're done with that first part. And then we're going to have plus 1/2 e to the negative 2x dx. Bring the 1/2 out front. And this is going to be the third time we do this integral. So the nice thing about integration by parts, if you're being consistent with how you choose dv, when you're going through this remaining integral is going to be, it's going to feel very similar, and you've probably done it at some point before in your work. So we've done this integral. This is going to be the third time now we've done this. So the integral of e to the negative 2x, we know what that is. So we have that constant multiple in front, and then the antiderivative is negative 1/2 e to the negative 2x. All right. So we just need to put it all together now. So what did we find before? Well, we found that our original integral, the one we're trying to do, was equal to all of this, negative 1/2 x squared e to the negative 2x, plus this integral that we just calculated. So let's fill that in. And I hope I remember this correctly. Nope. There we go. And then we fill in the piece that we just calculated. So we know this remaining integral is what we calculated right here. So we're just going to fill that in. So we end up with negative 1/2 x squared e to the negative 2x minus 1/2 x e to the negative 2x minus 1/4 e to the negative 2x. And we'll put our plus c constant at the end there. And there we go. There's our answer. Now, we could actually simplify that out if we wanted to, and it might not be a bad idea. So the nice thing about these exponential ones is you can always factor out the exponential. So in this, if we wanted to simplify this down a little bit, we could factor out negative 1/2 e to the negative 2x, just to maybe simplify it down a little bit. But it's fine to leave it like that. That's also correct. All right, so we saw how to use integration by parts to integrate inverse functions, and now we've seen it that there's cases where you have to do it twice, or maybe even more. So it's no coincidence that in this original integral, we had an x squared, and we had to do the integration by parts twice. So if we had like an x cubed, well, then you'd have to do it 3 times. All right, so we're going to stop there. Our next lesson is going to be on how we use integration by parts when calculating definite integrals. So we're going to just get a little bit more practice and just see how to kind of do the evaluation. All right, so we'll see you then. Bye-bye.